So let me welcome everybody to today's colloquium at Radboud University. You see our nice central building that of our university. Of course, we're now all distributed at our homes, and happy that we welcome colleagues from our university, but also from abroad, who are interested in the latest results of the Event Horizon Telescope that was presented yesterday. And I'm very proud that we have three of the leading scientists who've been really deeply involved in this work here as our speaker, working also in our department, and are willing to give a public lecture for you. Let me introduce them briefly. First of all, Monika Moscibrodzka, who is an assistant professor at our university. She came here already many years ago. She's now assistant professor. She came as a postdoc. She did her PhD in Warsaw, at the University of Warsaw. She worked at the Copernicus Center there. She moved then to Illinois, working with Charles Gami, leading theorists working on GRMHD simulation. Then she went to the University of Nevada and then came to Radboud. What makes her very unique in the world is she's one of the few people, in fact, a pioneering theoretician who is able to actually calculate radiative transfer in curved space-time, in general relativity. Polarization is a very difficult subject, not only observationally in radio astronomy, it's a very difficult topic, but also theoretically. And Monika pioneered some of the methods and that we're using now that enable us to calculate polarization around black holes. This is not an easy thing. I would not be able to do this, to be quite clear about this. Then we have Sara Issaoun, who is a PhD student. She did her bachelor at McGill University, then came to Radboud as a summer student, and then did her master here and her PhD. She really specializes in observational techniques, and she already, despite not even having finished her PhD, has a lot of leading positions within the EHT. She's been co-leading the calibration work in the EHT in the beginning. She has been at the telescopes observing, and she is leading some of her own observational programs, is actually in a number of committees already in the EHT, and was also deeply involved in the observational parts of getting this image. I forgot to mention that Monika is also chair of the working group for polarization. As a theorist, she was overseeing not only the theory work that's done, but also the observational part. And I think that's something that makes it very special. And then we have Alejandra Jiménez-Rosales, who came from Mexico originally, University of Mexico, National University of Mexico, then did her PhD at the Ludwig Maximilians University in Munich, working actually in the Max Planck Institute for Extraterrestrial Physics, in the infrared group, the group of Reinhard Genzel, with Jason Dexter as the direct supervisor. And after getting a PhD, she came to Radboud, and she already saw the excitement of the measurements that were done with gravity, where people saw infrared flares going around the black hole in the center of our Milky Way, and the polarization patterns that we see in this data. And now she witnesses the polarization in the Event Horizon Telescope data. So she sees it from both sides. And now I've talked enough, and I still don't see that YouTube, the link is working, which is a bit of a pity. And I nonetheless hand over to Monika to present her talk.
Thank you, Heino. I thought that you want to mention one more thing.
Oh, no, okay. I want to,
Yeah.
Of course, we have to say this is of all work done by the Event Horizon Telescope, and our participation has been made possible, of course, by our university, but also by the European Research Council, who funded us for a long time. And so we're grateful to that. And in fact, all the other European partners and partners in the EHT who made that all possible. Thank you.
All right. Thank you very much, Heino, for this very nice introduction, very detailed introduction. Good afternoon, everyone. I am really delighted to be able to talk to you today to give an introductory overview talk about the newest results from the Event Horizon Telescope, namely the discovery of magnetization in a ring of light around the black hole shadow in the galaxy M87. You know, before going into details that will be given by Sara and Alejandra, I would like to give a few remarks that will hopefully help everyone to understand what is actually visible in this image. But let's start from the beginning. What is the Event Horizon Telescope? It's a virtual telescope made of several elements which are spread across the globe, which, you know, they once in a while point towards M87 or the black hole in the center of our galaxy, and they collect light. All these elements, all these single telescopes in an array observe at the same wavelength that is equal 1.3 millimeter, which is close to radio waves. So all these elements, EHT telescopes, look more or less like radio antennas. And these antennas are, of course, not physically connected, as shown in the picture. Once the data is recorded at each site, it's taken to one place and combined into a data set that then can be used to construct this kind of images. And because effectively this telescope is as large as Earth, it has enormous resolution power that allow us to image objects as small as black holes. And in 2017, we observed with this telescope the core of M87 galaxy and also many other objects. And these observations in 2017 were good enough for the first time that to allow us to construct the image of M87 black hole shadow that you already saw 2 years ago. And we actually, back in 2017, because of very good weather conditions, EHT managed to observe M87 for 4 days. So we have actually 4 images of the black hole, not just one. But we always show April 11 as the best one because this, on this day, basically we had the most of the data collected. And since this initial discovery, we were pondering what is producing this ring emission, this plasma that we see glowing. You know, could be falling towards the event horizon, or could be on its escape route, or could be simply rotating around the horizon. Another open question is this black hole spinning, or, you know, how is this ring going to look like in the future? Finally, how is this ring connected to the jet that we see in M87, that the M87 core is producing? By the way, jets are often seen in black hole systems. These are streams of plasma, ionized matter, which are accelerated to speeds that are comparable to the speed of light. And they are sometimes so powerful that they can escape the black hole, but also the galaxy, and they traverse entire galaxy and propagate way beyond the galaxy. And this actually happens in M87. So what are the properties of the M87 ring measured back in 2019, where the ring is only 42 micro arcseconds in diameter? This is really small, corresponds to nearly, you know, the size of the black hole itself. Given the mass, we know, you know, how should this radius should be. It's almost perfectly circular, and it also has this brightness asymmetry. It's brighter on the south side. And finally, this ring has so-called very high brightness temperature. What does this mean? It means that approximately that plasma that is emitting this radiation is very, very hot. In fact, these electrons, these particles that are emitting light have thermal speeds that are approaching speed of light. We call such plasma relativistically hot plasma. This also means that this emission that we see in a ring is produced by synchrotron process. What is synchrotron process? So when the plasma is hot, it becomes ionized, and it will have free electrons. These charges will feel magnetic fields and gyrate around it. and the gyration motion is associated with the production of light. And we call this a synchrotron emission. And the synchrotron emission actually has this property that it's basically polarized. What is polarization in the first place? Well, what is light in general? It's a wave, it's an electromagnetic wave. The electric vector of this electromagnetic wave oscillates, and the direction of the oscillation is that we call it a polarization direction. And also keep in mind that light rays are made of many waves propagating together in packages. So if these different electromagnetic wave fields are oriented randomly with respect to one another, then this individual direction of polarization could average out to 0. Then the light means it's unpolarized. So in addition to polarization direction, we also have to think about polarization fraction, or in other words, how much fraction of light is oscillating in the same direction. And synchrotron radiation in particular can be up to 100% polarized. So all light waves can be nicely organized. So in comparison, for example, the natural light that our eyes see is unpolarized. All right. What can we learn from light polarization, specifically when we talk about synchrotron radiation? Well, imagine a magnetic field line, the blue stick on this plot, and imagine electron gyrating around it. This is the black dot. And the gray arrow shows the direction of emitted light, more or less. And the green tick shows the direction of light wave electric vector oscillation. So in this kind of simple situation, this electric vector, the green tick, would be at the 90 degrees, would be perpendicular to this magnetic field line. Now, what we see in the M87 image, and here you can see a scientific version of polarimetric image that we released yesterday. The ticks represent light electric field vector. So on the top of a gray background that represents light intensity, the tick direction is the electric field vector direction, and its color represents how much or what fraction of light is polarized. So in this case, it's only small fraction. It's 15% at most. Now, in our press release image, we show these polarization ticks in form of lines that are overplotted on the top of these intensity maps. This was done to make the image look more appealing. But here one has to only understand that these lines do not represent magnetic fields. They represent the direction of light wave oscillation as seen from our point of view here on Earth. Is the field, a magnetic field in a ring perpendicular to these lines? Not necessarily. The light we see in the images comes from a very deep gravitational potential of a black hole, and that wraps itself around the object due to gravitational, light-bending gravitational pull. So to understand this underlying magnetic field, we have to actually come up with some kind of theory. This should go to the next slide. All right. So basically, once we have a 3D model of magnetic fields around the black hole, using models of emission and transport of light in strong gravity, we can construct a model images. We then can compare those to real image and infer whether model is consistent with observations or not. From that, we can guess what is the geometry of magnetic field in M87 ring. And we found that in case of M87, these magnetic fields may be twisted, but they may have a significant so-called vertical component that is basically perpendicular to some accretion disk around this black hole. And you will hear more about this modeling from Alejandra. All right. And finally, why are we interested in magnetic fields around black holes in their shape and strength? Well, models of accretion flows onto black holes tell us that magnetic fields and magnetic forces are in control of how black holes swallow matter. They control how the matter infall occurs. The magnetic fields will also therefore impact how the source will be changing or evolving. And magnetic fields can be also strong. They can even stop matter from falling onto the horizon, and they can help the matter to escape into a jet. And we are actually very interested in finding out how this process actually happens in reality, because we see jets not only in M87 system, but also in many other galaxies out there. These jets could be very large structures reaching beyond their own galaxies, and they carry energy from the black hole, to entire galaxy. And now we have finally, another critical element of the story that can help us, to understand how these jets are formed. Okay, and then finally, before we move on to details, I would like to underline and stress that this image and this new results and the interpretation is a team effort. There are many people who contributed to this data calibration, analysis, imaging, and modeling. Not all of them are shown in this picture of a workshop that we held in Bonn back in 2019. But this is how this kind of science is being done. It's a team effort, really, and I would like to acknowledge that. Okay, thank you very much.
Thank you very much for this brief introduction, and I think we switch right away to the next speaker, which is Sara Issaoun. Sara, go ahead.
Yes, thank you. All right, so I'll be continuing from Monika, and I'll be talking more about the observational parts of our work. If there's one takeaway to get from my portion of the talk, is that it's really hard to do polarization. That is the main takeaway, and I'll show you a little bit why that is. So Monika talked a little bit about the EHT array. The Event Horizon Telescope, when we observed in 2017, when we collected our data, was made up of 8 telescopes at 6 different locations. We had 6 single dishes and 2 phased arrays. Because M87 is a northern source, the South Pole Telescope actually cannot observe it. So only 7 of them actually see M87. Now, what is the most striking thing if you look at our telescopes is that it all look completely different from each other. The reason for that is that our EHT team actually borrows telescopes. We don't build them to make our experiment. We borrow telescopes that have been designed for different radio science who just happen to be at the perfect sites for us to observe our radio waves at 230 gigahertz. And because they look so different, it's really, really hard to calibrate them, to make sure we understand them. Because they're not all the same, you can't just apply our knowledge of one telescope to all the other ones. We have to really understand each of them, how they behave, how they move, and how they observe. Now, what the EHT team did is actually equip all of these telescopes with receivers to observe at 230 gigahertz, with recording equipment in common, and also with what we call quarter wave plates that actually make all of these telescopes observe circular polarization, which means all of these telescopes observe the exact same polarization modes from the black hole, which helps us then combine the data in different polarization combinations and make what we call total light, linear polarization, and circular polarization data. So what we published in 2019 was our total light images, our total intensity, and what we're publishing today is, or yesterday, is our linear polarization information. So understanding our telescopes is a really important part of everything we do with the EHT. A large part of our telescope understanding was made before 2019 to publish our total light images. But for the last 2 years, one specific aspect was spent a long time to try to figure it out, and it's called polarization leakage, and it's underlined here. So from all these different effects that can mess up our data and actually corrupt it and contaminate it, there's one part that really affects polarization signal, and that is polarization leakage. The reason for that is that the polarization signal from the source is really weak, and so it is very sensitive to contamination. And because we observe also something that is directional, this direction of the wave oscillations, even any kind of leakage that may cause it to change direction would affect our conclusions. So it's very important to understand what is this leakage from all our instruments, how do we remove it, and what effect does it have on our images? So, and I can tell you this is really not an easy task. And we are perhaps working with the most complex radio interferometer that exists right now. And so it was really a really difficult and arduous and team effort to get here. So how do we do this? We use a technique called aperture synthesis to image with the EHT. We observe our source for a very long time, and Earth's rotation beneath our feet helps us fill what we call our coverage, our virtual mirror. And so we combine all these different data from in time and in space across our virtual mirror, and then our image comes together. What's nice is that as the Earth rotates, the source also rotates on the sky. So if we're trying to separate, for example, what is contamination from the telescope and what is actually signal from the source, this is where this effect is really useful for polarization calibration. So say you have your source that moves on the sky. Over time, it makes an arc on the sky for the telescope, but the contamination from the telescope itself doesn't move. It stays on the ground. So what we do is, using our data, we combine these different arcs from these different telescopes and then try to kind of triangulate in some way what is the contribution from the instrument from each telescope, and remove that, and then make an image of the true polarization signal that comes from the source. So this is what we did for our first step. Right after our big 2019 result, we got right back to work and we said, hey, now we've done total light. Let's look at polarization. Let's see what we have to show. We worked for about 2 months to try to get our softwares up to date to do polarization imaging. And we had our first attempt at making polarized images in July 2019. So just a couple months after a big announcement, we got right back to it, into working on new science with the EHT. So we met in Bonn in Germany for a workshop, and we split our teams into 3 software teams using 3 imaging softwares that we understood pretty well. So we have the EHT imaging software that was led by Andrew Chale at Princeton. We have the PulseSolve software that was led by Ivan Martí Vidal at the University of Valencia. And we have the LPCal software, which is developed by NREO, and an enhancement of it called GPCal, led by Jung-Ho Park from KASI in South Korea. So again, a very diverse team of researchers working on this with our different teams. And so at that workshop, we looked at polarization for the first time and imaged, using just our own user choices of what we should do with the softwares and the data to get an image. And what we got was a ring of the same size in our total light. And then for our polarized images, everybody got this kind of ring with a patch in the southwest. This was the first time we really saw images in polarization of M87 this close to the black hole. And it was really terrific that already we saw 3 softwares that were showing the same thing. And also our leakage terms, which you can see here, are really consistent between the 3 softwares. So we were already really excited. We said, hey, we finally see consistency between these different images. Now we really need to make sure we understand whether this pattern is real, right? And whether there's any introduction of any effects that may change this pattern, either from the instrumentation leakage or from the user choices from these softwares, these buttons of each software. So the next, so after that, of course, we celebrated, which Monika already showed. This was, the happy faces of people seeing polarized images of a black hole for the first time, which is freaking awesome. It's just so cool to be able to do that with the EHT. So of course, we're all really happy and glad that we were able to do this, but there's a long journey ahead. So the next step is to systematically test our software. So we had all these buttons, right, from all our softwares, and we want to make sure we choose the right buttons that give us the right answer, the answer we want. So we optimize our algorithm with an objective performance assessment to recover a truth image structure, which we can input, and the instrumental leakage, which we also input. So we created these 6 different data sets, which have different structures. So some are crescents. We have a disk here that doesn't have the shadow in it. And they all have different polarization patterns. Some are more complex. Some are kind of simple. Some have strong polarization. Some have weaker ones. And we wanted our softwares to try to reconstruct all of these. And we tested loads and loads of parameters to make sure we chose the ones that best represented the truth images, which we obviously knew the truth. Whereas for M87, we don't know the truth. So we want to make sure we objectively choose the right parameters that give us the truth. So we wanted a single imaging script per our 5 imaging softwares, so 3 imaging and 2 posterior exploration algorithms that give us these optimized parameters. So we tested tens of thousands of imaging parameters combinations systematically for all our software. We generated this synthetic data, this simulated data, where we know the truth image behind it. We tested all the parameters against our imaging method. We created images, and then we ranked them based on how good is the image reconstruction compared to the truth. And then the best ones, the best sets of parameters, are what we then took and applied on the M87 data to get an M87 image. So for our April 11 data set, this is what the best results were for our 5 softwares. And you can see here again, we have our 5 softwares. These are the 3 imaging ones, and we have 2 new posterior exploration ones, DMC developed by Dom Pesci at SAO, and Themis developed by Avery Broderick and his team at Perimeter Institute. And so all 5 softwares, again, gave a ring of the same size and with this patch in the southwest. So now we're saying, okay, we've had parameters that we've tested. We know that they're able to recover the truth images and they're robust and they get the right leakages and everything. And we still get this patch, the same one that we saw at the workshop in 2019. So we say, okay, this patch is real. But how much of this patch is real is the next question. So are these other features in our images actually real too? So the next step, so the average of these 5 images are what we had at the end, which is what we used as a representation for our famous image, which is this other representation Monika showed. So this one is April 11. And then we observed it for other 3 days. So these are the other 3 days as well. So you can see that this patch is consistent and we see it for all 4 days. So we know it's definitely real. But there was some other structure around the ring that we had to make sure was real too. So how do we check which part of the ring is real? So we produced what we called our 1,000 set images per software, where we actually changed the instrumental leakage that we input in our data. So say if the leakage we actually derive is slightly off, does that really change our image? So this is examples of what the leakages are sampled for each method. You can see quite a huge range of all these different numbers. We're looking at huge ranges of different leakages and their images in this 1,000 image set. So if we look at our set of images, this is kind of how much they vary. You will see that there's some variation here. The reason why there's this variation is because the polarization signal here is really, really weak. So it is the part we have the least certainty on. But you can see in our 1,000 set, there is a very prominent region here that doesn't change. It has the same amount of polarization fraction. It has the same polarization direction, this kind of spiral swoop. And it's robust to all our D-term changes or D-term tweaks. So this region is really what we're most certain about. And then we definitely don't trust the structure we see up here. So this gave us confidence in the structure we were able to see, because from this structure, like Monika said, we're able to infer information about the magnetic field. And so we wanted to make sure that whatever we infer is correct. So another nice thing is if you look at this distribution in our 1,000 set images along the ring, so if we just look at the intensity and the angle along the ring, we can see some differences. So all the softwares are, of course, consistent with each other, but across days, there's actually differences. So let's take one of the softwares and look at it. So this is how the intensity of polarization along the ring looks like. And at the beginning of our campaign on April 5th, the peak is here. And then on April 11, it has shifted. So you can see in our images that actually part of the ring, it starts brighter on the bottom. And then at the end of the campaign, it has moved to the west side. And this is really exciting because it tells us that there's actually evolution in polarization around the black hole. And obviously, variability is a really good way to test simulations, to test theoretical models. So it tells us that we're able to see variation in polarization and intensity and angle with the EHT, which is really exciting for new science in the future. So what can our images teach us about M87? I'll leave that to Alejandra to tell you all about it. And this is where I leave you off and tell you that polarization is really hard and it took us a long time to get here. Thank you.
Yeah, it was only, I think, like 15 minutes to explain 1.5 years of really hard work by many, many people. So it's only a small aspect of everything that has happened, but it was quite a marathon and heavy lifting that you all did. Alejandra, you might want to continue.
All right. So, hi everyone. Thank you so much for joining. My name is Alejandra Jiménez-Rosales. And in this part of the seminar, we're going to dive a little bit into what goes, into our modeling and how we compare our models to the observations such that we can learn a little bit about, the physics that are underlying this newly polarization pattern that we added to our ring. So I'd like to start here, where I show you a collection of, a few examples of models that we use to compare to the observations. So the idea is we have our library of models. We know all about our models, and we can quantify their properties and then compare to what we see in nature. And from these we can say which models work and which models don't work. But how do we actually come about and work this out? How do we simulate a black hole? Well, the setups that we use for our simulations are this. So we start with a black hole that may or may not be rotating, and then it's surrounded by matter that is orbiting, right? This is a plasma. And so we also add a magnetic field, and due to interactions with the matter and the magnetic field, we expect light to be emitted, synchrotron light, as Monika was mentioning. And so this light has to travel through this medium and eventually reach us, if it ever does. Another feature from this type of calculations is that often we get this ejected matter in the poles of the system, right? And we call these jets. So this is just simple schematic that I'm showing you here. This is a little bit more stylized. And so we can still see, all the different components. But I would also like to point out the different morphology of the magnetic field lines that are pictured here with white lines. And so we can see also how they're permeating the inside of the jet. So there's one element missing here, and that is the emitted light. So what we can do is we can also calculate images, right? We can place a synthetic camera that tells us what the black hole would look like. And so we can put our camera anywhere in space and then just point it towards the black hole and calculate images. And so here on the right, I show you an example of the types of images that we will typically get. And so we see this swirling matter that is rotating and it's going around this dark region at the center. And this is the area that we associate to the black hole shadow. Now, there are a couple of tricky things in this image. When you look at the material that is flowing, you might think that this is this orange ring on the left, right? But actually the image is a combination of the jet that is pointing at you, the disk that is behind you, and as a bonus, we also get emission from behind the black hole. And this is because the black hole bends space. So at the bottom of the slide, I show you an example where we have a slice of space. And just because we have a black hole there, the emission from behind is going to be bent. So if we apply this to our images, it means that the top part of our image is actually coming from behind. And we also get this a little bit from underneath the image. So that's a quirky fact about these images. The other one is that you see this asymmetry in the emission. And this is also because we have a black hole there at the center. So as matter is going around and light is being emitted, the side of the image in which light is coming towards you will actually be brighter as opposed to the side that is receding. So let's just take one of these snapshots. Press pause, and then we get these images, right? This is the total intensity. But we can also calculate what the polarization looks like for our models. And so this is what it looks like, right? The direction, the polarization here would represent with these white ticks that I showed you before also. And so the direction of the ticks tells you about the plane in which light is oscillating, right? This is polarization. And their length tells you just how much polarized that pixel is. And so these types of configurations, well, these ticks that are on top of these images we call polarization maps. Now, there are many effects that can modify the polarization in our calculations. So here, just to mention a few, we can look at the top panel. And so just the presence of the black hole. As I mentioned before, the black hole is going to bend space, right? So we have this disk, and then the back is going to be bent towards us. But this is not just a 2D effect. This happens in all directions. So if we were to have a photon or a light ray that is kind of traveling towards the black hole, and then it has to move in this deformed space. Now it can either go around the black hole once, twice, 3 times, and then maybe fall into the black hole or escape. And if this one reaches us, then just to show you there, the polarization is changed already, just by this geometrical effect that I'm showing you here, and due to the presence of the black hole. So this is one of the effects that we have to take into account when we're doing these calculations. Another one that I would like to mention is the one here on the right, where the properties of the matter around the black hole are important and they modify polarization. So we can change the temperature, we can change the density, we can change the magnetic field strength in our models, and this is going to reflect the change in the polarization. So for example, we can have a model where the polarization shows this very ordered pattern. So that's the top panel. And then we can also have, change something in the model that makes the polarization looks very scrambled. And so if you look at the background images, they look kind of similar, but the polarization is a dead giveaway that they are really different models, right? So this is another way in which we can use polarization to help us distinguish between different models which range in different properties for the parameters. And another one that I would really like to draw your attention to, this one is a big one, is the magnetic field configuration. So that is the bottom panel. So forget for a moment about the schematics that I'm showing you here. Just focus on the rings. And so if you look at the polarization patterns, the white ticks, they look different, right? The one on the left that says toroidal actually looks as if all the ticks went from, the center of the image outwards, right? In all directions. We call this radial. But when we go to a vertical case, it seems to be wrapping around the black hole. And the only thing that I changed between these two images was the magnetic field geometry. So we can see now in the schematics that, so here the magnetic field I represent with this blue, so on the left, these blue rings. And so polarization is perpendicular to each one of these. And this gives us these rays that are kind of going from the center of the image outwards. Whereas in the vertical case, the magnetic field is pointing upwards, and the polarization behaves differently. And so we can see right away how polarization is very intimately connected to what the magnetic field is doing. So once we take into account all these effects in our calculations and a few others, we arrive to the models in our library. And here I show you how these models would be viewed by a synthetic camera. But in reality, the EHT resolution is a little lower compared to this one. And so this is how the EHT would see our models, right? So now it's even more obvious that polarization is really helpful in telling all these models apart, right? This is the image that I showed you at the beginning. Now we've arrived to how we get our models. And so because these are our models, we can also calculate different quantities and compare these to what we see in observations. So we can look at the degree of polarization in the images. We can quantify the polarization pattern. And many of these models have these jets that are pointing towards us. So we can also calculate, for example, the energy that is contained in this ejected material. So when we do this is, for example, an example that I show you. So on the left, again, this is what we see. This is the same image that we have presented with the orange ring and the lines. But this one, as Monika mentioned, has a little bit more scientific information in there. So what we focus, for example, in our models is we compare to the length and the color of the ticks. We compare to how much, we quantify how much they are wrapping around the black hole, and other quantities, just to mention. And so here at the center, I show you some examples of successful models and some other failed models. And so we can see, for example, the bottom left model, that the ticks are not wrapping around, and they're also not the right color, right? This is too polarized. Whereas the one to the right of that, so bottom right, the ticks are a little bit wrapping around, not enough, but also this is highly depolarized, so it's too blue. Now in the top, we see two models that look a little bit similar, but not exactly right. And so they are still successful models because the numbers, when we do the calculation of these quantities, they are still within the allowed range of allowed range that we measure in our image. So they're still successful models. But still, applying all these restrictions to our wide library of models, in the end, tells us that the ones who survived were the ones who showed this strong magnetization close to the event horizon. And so what this tells us is that, very close to the black hole, we have these strong magnetic fields, strong enough that they are dynamically important, which, as Monika was mentioning, means that the black hole has a say in how the black hole is eating the matter, right? How the matter is falling onto the black hole. So just to bring the point home a little bit more, polarimetry is a very valuable quantity. So it adds more constraints to the models that we previously had. And so here I show you two examples of what we used to know with just the total intensity ring and what we now know with polarimetry. And again, so we have this magnetic field structure that is associated to strong magnetic fields close to the event horizon. And we're not yet sure how to connect the ring to the large scale jet, but we now have one more piece of the puzzle. And yeah, the future looks bright. So I'll leave you here with this very nice animation made by Sara and Monika. And yeah, I thank you very much for your attention.
Thank you so much for this this nice view of how black holes work. And as I said before, it's not simple. So it's a lot of theoretical work as well to actually describe that. Now, we already had a lot of questions that we answered in the Q&A section, but there may be other questions that you want to pose now. So if there are more questions, then please type them into the Q&A, and then we can try to answer here. I don't think we can have you talk, right? Steven?
I think that would be possible if you want.
Okay, yeah. Well, so if people want to if you want to say something, then Steven, may make this possible. Here's a question. What about black hole spin? I don't hear anyone talking about it. So who wants to talk about it now? Monika.
Yes, this is very important questions, probably one of the most important questions. How fast is this black hole spinning? Unfortunately, polarization is not that super sensitive to the value of the spin, as we know from the models. So in our library, we have several models that fit this image, but they have different spins. So at this point, we cannot really say for sure that the spin is this value with this error bar. So the spin is unconstrained yet for M87. That's why we don't talk about it.
Yeah, but there were some predictions for the future, right? If you look at variability.
Yeah, probably variability is, spin will control the variability. We would need to make multiple observations, probably, multiple days in row, not just, 4 days from beginning of the week and at the end of the week. So maybe from that in the future, we will be able to say something more about the spin. At this time, we don't have like a strong constraint. That's why we don't really talk about it.
So there's a question from Mark Kleinwald. Do you see any evidence for mass being ejected? So do we see evidence for the jet in those images?
We still don't know if this plasma is falling in or for flowing out. For that, again, I think we also need some more observations over different periods of time to say for 100% to be 100% sure what is this plasma doing. So at this point we don't know yet.
But I would argue that given that this is directly connecting to the jet, these are poloidal magnetic fields that we're seeing. This should be the launching point of the jet, right? So for all practical purposes, this is where the jet is anchored, right? Is that a wrong description, Monika, or?
One could say that, but I think this is still a little bit speculative statement. We know that for sure the magnetic field cannot be entirely toroidal, wrapped around the black hole. It has to have some vertical component, but I think this would require more research to find out exactly.
Well, that connects to the next question. What pieces of puzzle are still left to ascertain which models present reality as much as possible? So what else do we want to do we need to get?
Yes, so very crucial piece of information is present in data collected in the next year, in 2018. This data has more measured polarization at 2 more frequencies. And from that we can maybe have better estimates on the so-called rotation measure towards the towards the source, and this will help us to constrain the models better. So this is like a plasma effect. rotation measure is a plasma effect that additionally rotates these polarization vectors along the line of sight because of some, magnetic fields along the line of sight. So we have to figure this out in the future.
Okay, and thank you. And there are two questions which are slightly connected. Jamie Reed, how does the polarization allow us to determine how close to the event horizon the magnetic field is? And Frank Els, does the magnetic field come from inside the black hole or from things outside or at the event horizon? Maybe Alejandra, you want to comment on this?
Yeah, sure. So we expect the magnetic field to be there because the matter themselves is dragged it all the way into the black hole. And so we would expect all this area to be highly magnetized. Now, what we're exploring now is just how strongly magnetized this is. So the black hole would just be permeating the outer part the magnetic field would be permeating the outer part of the black hole. Yeah.
Yeah, but it would not go into the black hole, right?
Yeah,
so
exactly.
It would be in the plasma, would be surrounding it. And and we see it on scales of the photon orbit, more or less, right? So, or the innermost stable circular orbit, so a few short-slit radii. Yeah. It's Francesca Loy. In their models, is the observed magnetic field ejected in the environment, or is it confined to the ring? Well, I mean, it's sort of connected to the question we had before. But in the models, what does the magnetic field do in the models?
Yeah, so many of our models generate these jets, and the way this happens is because the black hole is surrounded by this magnetic field that then starts to wrap around and powers up the matter outside, like in the polar regions. This is how we believe the jets are formed. So yeah, they can be launched out into space.
Yeah, that's one of the big questions, of course. Yes. DC Adams, did you begin determining gravitational redshift near the event horizon of the black hole? So are there any effects of redshift?
I don't fully understand the questions, but we are observing almost at the same frequency. It's a monochromatic, to some degree, monochromatic image, so we cannot really measure any gravitational redshift or anything like that.
Yeah,
I'm not sure if this is the
probably
answer to this question.
I probably could say that the event horizon is infinite redshift. So that's what we see, right? So we see that infinite redshift, but yeah. How much are you able to generalize the results to other black holes? Do you expect a large variety of models to be valid for different black holes, or do you expect the majority of black holes to be similar? I have a strong opinion here, but I'm interested to hear your opinions. Monika, maybe, or?
Excuse me, I was answering some other question about space PLBI. Which one question is this from?
Let's do orally now. I mean, don't bother typing now. I think we'll stay orally.
All right.
The question was whether you expect a large variety of models to be valid for different black holes, or do we expect the majority of black holes to be similar?
I think they can be different. We don't know. This is something yet to be answered. We need more observations to find out, I think. For example, M87 and Sagittarius A-star comparison is interesting. We don't know if the accretion and jet formation look similar in these two sources, but this is something probably that we can answer in the near future, like soon. But other black holes out there in the universe, we believe that accretion physics and jet physics is similar in the entire universe, but this is to be tested in the future.
It's probably always a question to ask what is different and what is similar. You know, all people are alike more or less, but they all have their characteristics, right? So
different black holes accrete matter or eat matter at different rate. For example, so Sagittarius A star is on starvation, and M87 is swallowing, significantly more matter. So there is a difference between these two systems in this respect, for example.
But still, luckily, I mean, black holes are simpler than us people. So, so maybe less variety than among people. Yeah.
They could have different spins, for example, right? That would make them different.
Yeah, there was a question on space VLBI. Did you answer that?
Yes, there are many people is actually thinking about imaging black holes from space by launching antennas into space and having a big array in space. But I think this is a matter of future, maybe next 20, 40 years. I would say, I know, yeah.
Yeah. I hope before, certainly after my retirement, I hope before my death, but you never know what's first. So
that's very expensive experiment. So it also depends on funding.
But at least you get very high resolution. I mean, and you get very high image quality. So it's definitely, I mean, that will bring the entire field to a completely different level. Questions about funding. What are the expectations for funding the continuation of your research, especially since so many people and institutions are involved?
We leave it to you, Heino.
Well, actually, you brought in more funding now, so we're still looking for funding. There is funding at different places. A good thing it's a broad collaboration, so there are many people working on it. And we hope to also secure more serious funding. In fact, we have submitted proposals again, so we don't give up. Let's see. Yeah, well, a question that often comes up, maybe now to Sara, because she hasn't answered any of them yet. What is so observationally so handy about M87? Why everything is published on M87 and not on other black holes?
Yeah, that's an easy answer. M87 is the best. So why M87? So we have our two sources that we observe with the Event Horizon Telescope, M87 and Sagittarius A star. That's because they are the biggest black holes on the sky. Their angular size is big enough for us to be able to image with the EHT, with our Earth-sized telescope. So there are only two black holes reachable with an Earth-sized telescope to image its shadow. The reason why we published M87 first instead of Sagittarius A star is because it's about 1,000 times more massive than Sag A star. And the more massive a black hole is, the slower time is around it. And so the gas around it moves much slower than for Sagittarius A star. So if we stare at it for about 8 hours, which is the length of our daily observations with the EHT, the gas doesn't move that much. So we can actually use this technique that I talked about called aperture synthesis to combine measurements over time and over spatial coverage and actually make an image. For Sagittarius A star, the gas moves on timescales of minutes. So if you look at it over 8 hours, every few minutes it looks different. So if you're trying to make an 8-hour image, it's going to look like a blur. Think of it like taking a long exposure, right? So M87 is like taking a long exposure image of a person just sitting still, like an adult sitting still waiting to have their portrait. And for Sag A star, it's like taking a long exposure of a running wild toddler. So if you try to do that, you'll end up with just a giant blur. So in order to analyze that data, because it's so variable, we need to obviously develop new techniques and new methods to cross-check. And as you saw for my talk, cross-checking and making sure we understand each portion of the image is a really important and lengthy process for us at the EHT. Understanding our instrument, understanding whether we know the entire signal that comes from the source and how it translates into an image are a really crucial part of our scientific journey. And so for Sagittarius A star, it's much more lengthy to get to this point. But it is coming, and we're working on it really hard, and we worked on it in parallel with our polarization work. And we hope to have something to show you for Sagittarius star really soon.
Yeah, we'll have two or three more questions, and then we'll wrap up. But maybe stay with an observational question, Sara. The polarization and variability, Francesco Travaglini asks, the changes of a 4-day period. Are the data already fully processed, investigated concerning this possibility? Or could it be that we're seeing effects of something on the line of sight that changes the polarization? Or is the source actually too small that we could actually see that variability?
Yeah, so the variability we're observing is at the black hole. So it is in the structure of this polarization, polarized light that comes from the gas around the black hole. And we see variability also in our total light. We see some changes in the brightness distribution along the ring over our 6-day span of our observations. And we see also changes in polarization. What is a difficult task is because we only have 4 kind of snapshots. It's not enough for theoretical models to be able to really pinpoint what exactly is changing. So is it really like one part that is moving to another part? Is it one part that gets brighter or dimmer? That is still difficult to analyze. And so we hope with more observations, or as Monika said, more frequent observations of the source, many days in a row, will actually help us trace more clearly these kind of variability and be able to actually pinpoint what is really changing in our theoretical models.
Yes. Will the data actually be made public eventually?
Yes, it will definitely be made public. It's a very important part of our process to make our data available for cross checks.
Yeah. And then maybe last questions, I combine the two, bit more speculative. We usually invoke magnetic fields if we don't know something, but it seems here magnetic fields are really, really crucial to get jets launched. Maybe Monika or so, are there ways to launch the jets without magnetic fields? And are there plans to image sources, or can we image sources without jets actually?
I think synchrotron emission for the ring is the simplest explanation, and I cannot think about anything else. So it has to be magnetic field producing this polarization. You can also produce polarization via reflection of light from some surface, but I don't think this is the case here. This ring has such a high brightness temperature that this is for sure synchrotron emission. So, and there are theories for jet production without magnetic fields, but here we for sure see this magnetic field. So, these other theories would not survive this new observational constraint. Yeah, and what was the second one?
Well, can we look at non-jet sources?
Yes, so for example, galactic center, supermassive black hole, it's a radio source, just like M87, but we are not entirely sure if this black hole has a jet or not. So maybe, in the future we'll find out. It's definitely possible to have magnetic fields around the black hole that are not producing a jet. For example, if magnetic fields are turbulent, like tangled up, you can still see this kind of synchrotron emission and polarization, but no jet. Yeah, so it's a possible situation, but we'll see.
Yeah. I think I don't see any other questions, and everything else has been some thanks here. There's some more coming in, but last question, Monika. I'll put you on the spot here, or actually Alejandra. Let me ask Alejandra, because Monika has been answering more questions yet. Can we rule out spin zero already?
Oh, that's a tough question. If we want to associate the ring and launching magnetic fields and launching this jet to the larger scale jet, then no, we need the spin. But I think so far yeah, we have had models that could have this spin 0, and they could also satisfy the constraints. So I guess we don't know yet. But yeah.
Yeah, but I think we are leaning towards spin, but the final proof is still missing indeed. Yeah. Which is good, which is enough work for us to do in the future. I think the spin is a big prize, as Monika said before, one of the big questions to answer. Thank you all for watching. Thank you particular to the 3 speakers who've been not only working very hard, but also been very proudly presenting it today and very capable presenting that to us. Thank you for communicating this and being available for these questions. And they're actually all on Twitter, so if you bug them with questions, they actually still tend to answer, even though it has been a lot in the last couple of days. But it's something I think we like to do. There'll be more news in the coming months. There are many other data sets that are still being worked on, not only ZJ-Star and M87. So EHT is fully busy and functioning, and we still have a lot of fun. I wish you a good afternoon, and hope to see you back, hopefully at some point in person, either in our university in the Netherlands or somewhere around the world where you are right now. Bye-bye.